Understanding behavioral metric learning in Deep RL. Here's a question. Imagine you're training a robot arm to pick up a cup. You feed it camera images as input. Now someone pastes a random YouTube video as the background behind the cup. Should the robot care? Of course not. The background has nothing to do with the physics of grasping. The cup is still there. The arm still moves the same way. But here's the problem. A standard Deep RL agent doesn't know that. Its neural network sees every pixel. The background, the lighting, the camera angle, all of it floods the observation. The agent has to figure out on its own what matters and what doesn't. The field of behavioral metric learning tries to solve exactly this. The idea is to teach the agent a distance function, a metric that tells it, these two observations are essentially the same, because the physics behind them is identical, even if the pixels look completely different. If we can embed that metric into the agent's representation, it becomes naturally robust to irrelevant noise. Sounds elegant, but does it actually work? That is the central question of today's paper. Understanding Behavioral Metric Learning, a large-scale study on distracting reinforcement learning environments, published in the Reinforcement Learning Journal in 2025 by Ziyan Luo, Tianwei Ni, Pierre-Luc Bacon, Denoise Precup, and Precup Si from Mila, McGill, Université de Montréal, and the University of Toronto. This paper doesn't propose a new algorithm. It's something arguably more valuable. It's a systematic, large-scale audit of 5 state-of-the-art metric learning methods, tested across 370 task configurations, with a brand-new evaluation framework that directly measures the denoising ability the methods claim to provide. And the findings are surprisingly sobering. Here's the roadmap for today. We'll start with the background on bisimulation and behavioral metrics. Then we'll walk through the unified framework the authors used to analyze the 5 methods. We'll cover the new evaluation tools they introduce. Then we'll go through the experimental results, the case studies, and finally the major findings and what they mean for the field. Let's go. Background, state abstraction and bisimulation. To understand why behavioral metric learning exists, we need to start with a fundamental challenge in RL. High-dimensional observations contain far more information than the agent actually needs. In most environments, especially robotic control, the true physics of the system is governed by a compact, low-dimensional state, joint angles, velocities, positions. But the agent doesn't see that state directly. It sees raw observations, pixels, sensor readings, that mix the task-relevant state together with task-irrelevant noise. Background textures, lighting variations, sensor jitter. These are distractions. The formal framework the paper uses to model this is the exogenous block MDP, or EX-BMDP. Here's the key idea. The full observation is generated from a latent state Z, which factorizes into 2 parts. S, the task-relevant state that actually drives the physics and rewards, and Xi, the task-irrelevant noise that evolves independently. The noise doesn't affect rewards. The noise doesn't affect how the system transitions. It's purely a distraction. The ideal encoder would strip away Xi entirely and return only S. The paper calls this the oracle encoder phi star. We can't access it during training, but it defines the target we're aiming for. Now, how do we define whether 2 observations are behaviorally equivalent? That is, whether they correspond to the same underlying task-relevant state and should get the same representation. This is where bisimulation metrics come in. Introduced by Ferns, Panangaden, and Precup in 2004 and 2011, The bisimulation metric defines a smooth distance between states. The key idea is recursive. Two states are close if their immediate rewards are similar and their next state distributions are close, where close is again measured by the same metric. This self-referential definition captures long-term behavioral similarity, not just one-step reward differences. The bisimulation metric has a beautiful theoretical property in the EX-BMDP setting. For any two observations x and x plus that share the same task-relevant state, meaning phi star of x equals phi star of x plus, the bisimulation distance between them is exactly 0. They're behaviorally identical. If we could learn this metric perfectly, our encoder would completely ignore noise. In practice, computing the exact bisimulation metric is intractable. It requires solving a fixed-point equation over all actions and all state pairs. So the field has developed scalable approximations. The most widely used is the policy-dependent bisimulation metric, or PBSM, introduced by Castro in 2020. Instead of taking the max over all actions, PBSM restricts behavioral similarity to the current policy. Cheaper to compute, but it comes with a theoretical trade-off we'll discuss later. The isometric embedding framework. One of the conceptual contributions of this paper is unifying 5 different metric learning methods under a single framework. They call it the isometric embedding framework. Here's the core idea. We want our encoder phi to map observations into a representation space such that distances in the representation space exactly match the behavioral metric distances in the observation space. An encoder with this property is called an isometric embedding. Formally, the distance between two representations, phi of x1 and phi of x2 in representation space, should equal the target behavioral metric distance between x1 and x2 in observation space. Why does this matter? Because if the encoder is a perfect isometric embedding with respect to the bisimulation metric, then two observations with 0 bisimulation distance, noise-equivalent observations like x and x plus, will also have 0 representational distance. They'll get the same embedding. The encoder must denoise. Now, let me briefly explain the most important design choices that differ between these methods, because these differences are exactly what the paper investigates. The first is how each method approximates the reward distance, dr. MICO and SIMSR use the absolute difference of rewards. DBC and DBC normed use the Huber distance, which is less sensitive to outliers. RAP goes further. It derives a better approximation by accounting for the variance of rewards under the policy, not just the mean. The second is how each method approximates the transition distance, dt. DBC, DBC normed, and RAP assume a Gaussian transition model and use the closed form 2 Wasserstein distance between Gaussian distributions. MICO and SIMSR instead use sample-based approximations, which avoid the Gaussian assumption but introduce different kinds of bias. The third is normalization. DBC has no normalization. DBC normed applies max normalization, constraining representations to lie within a bounded range. SIMSR applies L2 normalization, forcing representations onto a unit sphere, which converts distances to cosine distances. MICO uses layer norm in pixel encoders. This seemingly minor choice turns out to be one of the most important factors in the entire paper. Study design, noise settings, and the denoising factor. Here's where the paper makes its first major methodological contribution. Prior work evaluates metric learning methods almost entirely by looking at final return. How much reward does the agent accumulate? The problem with this approach is that it conflates many things. Return could improve because of better denoising, or because of better optimization, or because of the architectural choices like normalization, none of which has anything to do with metric learning itself. The paper takes a more surgical approach. First, it uses a much broader range of noise settings than prior work. Most previous papers only test on grayscale video backgrounds. This paper tests 6 distinct noise types: clean environments, baseline, IID Gaussian noise, colored images, grayscale images, colored videos, and grayscale videos, plus a challenging state-based variant with random projection. This spectrum allows the paper to identify which noises are genuinely hard and which ones prior work has been misleading us about. Second, it separates in-distribution, ID generalization, from out-of-distribution, OOD generalization. In ID evaluation, the noise during training and testing comes from the same distribution. In OOD evaluation, the training noise and testing noise are different. For example, the agent sees one set of video backgrounds during training and an entirely different set during evaluation. Prior work focuses almost exclusively on OOD, but the paper argues that ID generalization is equally important and tests both. Third, and most importantly, the paper introduces the denoising factor, DF, a direct quantitative measure of how well the encoder filters out noise. The idea is inspired by triplet loss in contrastive learning. For each anchor observation X in the agent's trajectory, you construct 2 companions, a positive example X plus that shares the same task-relevant state as X but has different noise, so same robot position, different background, and a negative example X minus that is just a random different observation from the trajectory. A well-denoising encoder should assign small distance between X and X plus, their equivalent, and large distance between X and X minus, they're genuinely different. The denoising factor is then simply the normalized gap, negative distance minus positive distance divided by their sum. It ranges from -1 to 1. A value of 1 means perfect denoising, the oracle encoder. A value of 0 means the encoder can't tell positive from negative at all. A negative value means the encoder is actively inverting the correct ordering. Fourth, to truly isolate whether metric learning itself causes any denoising, the paper introduces the isolated metric estimation setting. The idea is elegant. Instead of training a metric encoder together with the RL agent, where all the losses are tangled together, train a completely separate metric encoder, phi tilde, that is influenced only by the metric loss. The RL agent continues learning normally with its own encoder phi and its own RL objectives. The metric encoder phi hat observes the same data, but is updated only via the metric loss, with gradient backpropagation blocked between the two. This allows a clean, fair comparison. Given the exact same data and the exact same SAC agent policy, which metric loss produces the most denoising, independently of everything else? Let's go through the main benchmarking results. The paper evaluates all 7 agents, SAC baseline, Deep MDP baseline, and 5 metric learning methods, across 20 state-based DMC tasks with 10 IID Gaussian noise configurations and 14 pixel-based DMC tasks with 6 noise types. That's 370 total task noise combinations. This is the largest evaluation of behavioral metric learning methods to date. Let me walk you through the 4 most important findings. Finding 1. SimSR wins on state-based tasks. RAP wins on pixel-based tasks. In state-based domains with IID Gaussian noise, SimSR consistently achieves the highest return and the highest denoising factor across almost all noise levels. This is surprising. SimSR was originally designed and evaluated only for pixel-based tasks. The paper's state-based evaluation is entirely novel for this method. In pixel-based domains, RAP performs best overall. It handles the diverse noise backgrounds better than the other metric learning methods across most task configurations. Finding 2. SAC and DeepMDP are surprisingly strong baselines. This is perhaps the most uncomfortable finding for the metric learning community. SAC, the plain soft actor critic with no metric learning at all, and DeepMDP, which uses self-prediction and reward prediction losses, but no explicit metric, consistently match or outperform most of the dedicated metric learning methods. DBC, the most commonly used metric learning baseline in the literature, consistently performs worst among all 7 agents. Finding 3. Common benchmarks are too easy. The paper finds that the noise settings most commonly used in prior work, varying the dimension of IID Gaussian noise and grayscale video backgrounds, add only marginal difficulty compared to clean environments for the best-performing agents. Well-tuned methods like SimSR and SAC show minimal performance drops as noise dimension increases from 2 to 128. Similarly, grayscale video backgrounds are barely harder than clean backgrounds for SAC. This is a significant methodological critique. If the standard benchmarks are easy, then a method appearing to handle distractions might simply be doing fine on a task that wasn't actually hard to begin with. What does remain challenging? 2 settings. IID Gaussian noise with random projection in state-based domains, which linearly mixes task-relevant state and noise, making them impossible to separate without proper matrix inversion, and IID Gaussian noise in pixel domains, which is the hardest pixel-based setting. Even the best methods struggle here. Finding 4. Performance varies dramatically across individual tasks. Aggregated scores mask a lot of variance. RAP excels at reacher/easy. MICO does well at point_mass/easy. DBC normed is competitive on pendulum/swing up. No single method dominates across all tasks. This underscores the paper's point that broad evaluation across many tasks is essential to draw any reliable conclusions. Case studies. What actually matters? After the broad benchmarking, the paper drills down into what actually drives performance. It identifies 2 design choices that matter far more than the specific metric used: layer normalization and self-prediction loss. Layer normalization, the single most impactful change. Table 2 in the paper is one of the clearest results I've seen in an RL evaluation paper. For each of 6 carefully selected tasks, ranging from easy to hard, the authors take every method and simply add layer norm to the representation space. That's the only change. The results are dramatic. DeepMDP, the no-metric baseline, jumps from 168 to 926 on finger/turn_hard, from 31 to 195 on hopper/hop, from 347 to 776 on walker/run. And crucially, DeepMDP with layer norm is now competitive with SimSR, the best metric learning method on most tasks. A simple normalization trick applied to a method with zero explicit metric learning essentially catches up to the state of the art. This pattern holds across nearly all methods. Adding layer norm improves both return and the denoising factor for almost every agent on every task. The one exception is that DBC still struggles even with layer norm, suggesting its fundamental metric formulation has other issues. Self-prediction loss, the second key driver. The paper conducts a focused ablation on SIM-SR, stripping away the self-prediction (ZP) loss to isolate its contribution. SIM-SR, in its default form, uses ZP loss as an integral part of metric estimation. The transition model used to compute the transition distance term is trained via ZP. When the paper removes ZP from SIM-SR, what they call SIM-SR, basic, no ZP, performance collapses dramatically on hard tasks. On hopper/hop, the reward drops from over 200 to near zero. On finger/turn_hard, it drops from 885 to below 200. The denoising factor drops correspondingly. What this tells us, much of SIM-SR's success is not coming from the metric itself. It's coming from the self-prediction loss that trains the transition model used inside the metric computation. The metric is along for the ride. Adding a reward prediction, RP, loss to SIM-SR, on the other hand, provides only modest gains, suggesting that reward prediction alone is not a critical driver. Isolated metric estimation. Does the metric actually denoise? This is the most conceptually novel part of the paper. Even after the benchmarking and case studies, we still haven't answered the core question cleanly. When we strip everything else away and look at the metric loss alone, does it actually produce better denoising encoders? The isolated metric estimation setting answers this directly. The setup. A SAC agent with layer norm runs normally, collecting data. Separately, isolated metric encoders, phi tilde, are trained on that same data, one per method, but each phi tilde is updated only by its specific metric loss. No RL loss, no ZP loss, no RP loss, pure metric learning. Then the denoising factor of each phi tilde is evaluated and compared. The findings are striking and somewhat deflating for metric learning advocates. Finding 1. Metric losses alone provide some denoising, but less than ZP alone. When you compare the DF of isolated metric encoders to an isolated encoder trained with just the ZP loss, the self-prediction objective from DeepMDP, which is not a metric loss, ZP alone consistently outperforms most metric losses in terms of denoising factor. The metric loss provides some signal, but the dynamics prediction signal from ZP is stronger. Finding 2. Adding a metric loss on top of ZP doesn't help. When the authors add a metric loss jointly with ZP on the isolated encoder phi tilde, the DF generally doesn't improve compared to ZP alone. The metric loss is providing essentially redundant information that ZP already captures. Finding 3. Layer norm dramatically improves DeepMDP in isolation. Adding layer norm to the isolated DeepMDP encoder phi tilde substantially boosts its DF, both for the version with and without RP loss. But for the metric learning methods, the same layer norm addition provides only modest gains. Again, normalization matters more than the metric. Finding 4. MICO's DF is theoretically bounded below perfect. MICO uses what's called an independent coupling in its transition distance term, which means it can assign a non-zero distance to two observations that share the same task-relevant state. This is the theoretical reason why MICO's DF in the isolated setting remains systematically lower than BSM-based methods. The theory predicts it, the experiments confirm it. UdeM generalization and final findings. The paper also evaluates OOD generalization, the setting most prior work focuses on, and produces two important findings. First, static image backgrounds are harder to generalize to than video backgrounds, the opposite of what you might expect. When an agent trains on a grayscale video background and is tested on unseen grayscale videos, performance drops are modest. But when it trains on grayscale images and is tested on unseen images, all methods struggle significantly. The reason is intuitive. Video backgrounds provide temporal variation during training that helps the model learn to distinguish background from foreground. A fixed image provides no such learning signal. The background could just as well be part of the observation structure. Second, and this is the sharpest finding for the OOD setting, in the widely used grayscale video OOD benchmark, even SAC and Deep MDP show low reward difference between ID and OOD evaluation. The gap between training performance and test performance is small, even for the no-metric baseline. This calls into question whether metric learning is actually necessary to achieve what prior papers have claimed as evidence of its superiority. Key findings and takeaways. Let me now crystallize what I consider the 5 most important takeaways from this paper. Takeaway 1. Metric learning methods don't consistently outperform non-metric baselines. Across 370 task configurations, Deep MDP, which uses no explicit behavioral metric, and SAC, which uses no auxiliary loss at all, consistently match or beat most dedicated metric learning methods. DBC, the most cited metric learning baseline, is the worst performing method overall. This is a serious empirical challenge for the field's narrative that metric learning provides reliable benefits. Takeaway 2. Layer norm is the single most impactful design choice, and it's architectural, not metric specific. Adding layer norm to the representation space dramatically improves both return and denoising factor for all methods. It takes a poor method like Deep MDP and makes it competitive with the best metric learning algorithms. This means much of what prior work attributed to the metric is actually coming from normalization. Takeaway 3. Self-prediction loss, not metric loss, drives denoising. In the isolated setting, ZP loss alone provides stronger denoising than most explicit metric losses. Adding a metric loss on top of ZP doesn't help. The dynamics prediction signal in ZP is the key ingredient. The metric loss wraps around it without adding much. Takeaway 4. Common benchmarks are too easy. Grayscale video backgrounds and varying Gaussian noise dimensions add little difficulty for well-tuned agents. The paper identifies IID Gaussian noise on pixel domains and random projection noise on state domains as genuinely challenging benchmarks that better discriminate between methods. Future work should adopt these. Takeaway 5. Theory-practice gaps are real and multi-layered. The bisimulation metric has perfect denoising in theory, but every practical approximation, PBSM, MICO, DBC, introduces gaps that undermine this guarantee. Off-policy reward sampling, approximate transition models, and policy dependence all chip away at the theoretical denoising property. The paper makes these gaps explicit and rigorous for the first time. Summary. This paper is a valuable and necessary corrective to a growing body of work that has perhaps been overclaiming the benefits of behavioral metric learning. It doesn't say metric learning is wrong or useless. It says the field has been measuring the wrong things, using benchmarks that are too easy, and attributing gains to metrics that actually come from normalization and self-prediction. The open-source codebase the authors release is a genuine contribution, a modular, reproducible platform that unifies all 5 methods under the same framework and hyperparameter conventions, making future comparisons much more rigorous. What does this mean for practitioners? If you're working in a noisy observation setting, the evidence suggests you should add layer norm to your encoder, include a self-prediction loss, and then consider whether adding a metric loss provides any additional benefit, because in many settings, it doesn't. And for researchers, the paper points to clear directions. Design metric objectives that truly add value beyond ZP and layer norm. Test on harder noise settings, particularly pixel domain Gaussian noise and random projection, and evaluate denoising directly, not just return. If you want to read the paper yourself, it's published in the Reinforcement Learning Journal 2025, and the codebase is open source on GitHub. I'll link both in the description. If this deep dive was useful, please subscribe and let me know in the comments which metric learning methods you've used in practice and whether the results here match your experience. See you in the next one.